Okay, class, welcome to the next math lesson. Today we are going to be working on Module 1, Lesson 9. And this is about something called scientific notation. So for this lesson, you will need pages 85 through 93 of your book. So make sure you have those out with you and ready to go. Now, scientific notation is an easier way to write really big and really small numbers. Some numbers are so big and so small that it's hard to write them, it's hard to do math with them, and so people all over the world have decided to use scientific notation to make things standardized, to make things a little bit simple. So very large and very small numbers can be written with scientific notation. As an example, let's look at a very small and a very large number. So for an example, let's talk about how many stars are in the universe. Stars in the universe, at least that we're aware of. If I were to write this in the number of stars in the universe in standard form, it would look something like this. I think that's it. 60 some number, like that. Obviously that's a huge number. With scientific notation, you can, instead of writing that, you can write like that way, or you can just write 6 times 10 to the 22nd. Because this way tells me it's a 6 that is 27 place values away from the decimal. So here's the decimal. The 6 is 27 place values away from the decimal. Remember, 10 with an exponent is a place value. So 10 to the 22nd means 22 place values. So this 6 is 22 place values away from the decimal. So I know which one I would rather write because this one took me about 30 seconds and I had to check my work and count the number of zeros over and over and over again just to make sure I had the right number. This one did not take me so long. So that's a very big number that it works with. We can also come up with a very small number that we use scientific notation for. And for this, I'm talking about, let's talk about something super small, an electron. Modern society is based off electricity. Electricity is the movement of electrons. So when we talk about one electron, the mass, the size of it, this is the mass of or the approximate mass of an electron. There it is. That is a lot of zeros behind the decimal. That is a very, very, very small number. We can write it that way. Or you can write 9 times 10 to the negative 31st. Much easier to write scientific notation. We like scientific notation. It makes really big and really small numbers easier to write, easier to understand, and easier to use in math. Now, the 9 is 31 places away from the decimal, 31 place values away. But it's on the other side of the 6. It's smaller than the decimal. That's why it's negative. Remember, negative exponent means smaller. So let's talk about how to write. Now that we've seen the use of scientific notation, let's talk about how to write scientific notation. What are the rules? What are the style things that you should follow Now remember, scientific notation is scientific. It's worldwide. So people all over the world have agreed on how to do this. So the format of style notation, you have D, which is a number, times a 10 to the n power. Now let's talk about what each of these pieces mean. The D is a decimal number, hence why they picked the D, between 0 and 10. So it cannot be smaller than 1, it cannot be bigger than it cannot be 10 or bigger. It has to be a decimal number between 0 and 10. 1 and bigger or smaller than 10. Also, next part of scientific notation is the multiplication symbol. It has to have multiplication. Scientific notation is multiplying. It is not dividing, it's not adding, it is not subtracting. It is multiplication. The 10 has to be there. It has to be a 10. The base is 10. The base is 10 because that is what place value we use on Earth. We use base of 10. So because 10 means place value, this has to be a 10. Our place values are based on 10. So scientific notation uses 10. The n is what's called the order of magnitude. And we did talk about magnitude in lesson 7. So order of magnitude. In other words, the 10, the order of magnitude, remember magnitude means size. So the order of magnitude is how many place values the number D, the decimal D, changes. It tells us how many place values the decimal D changes. Or another way to put it, how many spaces the decimal moves. How many spaces the decimal moves. So you can talk about changing place value, or you can talk about changing where the decimal is. That's what the order of magnitude tells us. And remember, when we're talking about the order of magnitude, a positive order of magnitude makes a number larger, and a negative order of magnitude makes a number smaller. That is why in our examples, the number of stars is a very large number, so the order of magnitude is positive. An electron is very, very small, so the order of magnitude is negative. So you have to pay attention to what the order of magnitude is to know what size of a number you're dealing with. So let's really quickly summarize the rules of scientific notation. There are 3 rules for scientific notation that you need to know about that we'll be referring back to today. Rule number 1, D must be between 1 and 10. The math way to say this is D has to be greater or equal to 1 and less than 10. Greater than or equal to 1 and less than 10. We'll look at some examples in just a minute to let you know what that looks like. Rule number 2, scientific notation must be written as multiplication. Scientific notation must be written as a multiplication expression. Number 3, rule 3, the base of the exponent must be 10 because we live on Earth and we work in a base 10 system. Every place value is another 10. The tens place is a 10, the hundreds place is 2 10s, the thousands place is 3 10s. We work with base 10. So the base of the exponent must be 10. Let's practice some of these rules real fast. Keep your rules page handy. Remember, you are writing down the notes with me so that you have something to refer back to. Keep the rules for scientific notation next to you. You will need them in just during these first 6 exercises. So, exercise 1. For these first 6 exercises, you have to tell me, is this scientific notation? So look at exercise 1. Does it hit rule 1? Is the number bigger than 1 and less than 10? Yes, this is 1.908. 1 is a single digit number. It works. Rule number 2, is it multiplication? Yes. Rule number 3, is the base 10? Yes, it follows all 3 rules. Yes, that is scientific notation. Exercise 2, is this scientific notation? We'll check with rule number 1. It is D between 1 and 10? And no, D is smaller than 1, so it does not work. No. It breaks rule 1 because D is less than 1. You can't do that. That is not scientific notation. You'd have to change this. Exercise 3. Is this scientific notation? Is D bigger than 1, less than 10? Yes, it is. 7.99, bigger than 1, less than 10. Is it multiplication? Yes. Is the base 10? Yes. Exercise 3 is scientific notation. Exercise 4. Check rule number 1. Is D bigger than 1 and less than 10? Yes. 4 is bigger than 1, less than 10. Rule number 2. Is it multiplication? No. This is not scientific notation. This exercise 4 breaks rule 2. It must be a multiplication statement. Exercise 5. This one actually breaks 2 rules. Because if you look, D is 18, and that is bigger than 10. It has to be less than 10. Also, this breaks rule 3. The base is 5, not 10. So this breaks rule 1 and rule 3. The D is too big and the base is not 10. Exercise 6 follows rule 1 because 8 is bigger than 1 but smaller than 10. It is multiplication for rule 2, and rule 3, the base is 10. So yes, this is scientific notation. So hopefully after these 6 exercises you have an idea about the 3 rules and you know what scientific notation looks like. For our next exercise, we're going to start using scientific notation, showing you how it can help you with actual math work in the real world problems. Keep the rules next to you though, because they will be useful to refer to. So, exercise 7, we're going to start with exercise 7. It's multiple part. There's 3 parts. We're starting with part A. There is a table for all exercises 7 and 8 talking about different states. We have California, New York, Texas, North Dakota, Vermont, and Wyoming. And we see the state debt and we see the state population. And these are the 3 most populous states and the 3 least populous states. For exercise 7, part A, it's asking what is the sum of the debts for the 3 most populous states? And it wants us to answer in scientific notation. So sum means to add, and the 3 most populous states are going to be the first 3 on the list: California, New York, and Texas. So to find the sum of this, we need to add California, New York, and Texas. and we are adding the debt. So look at the debt column, and we are adding those three numbers. Already, you can see that there is a lot of writing involved when we are not using scientific notation, because I have to write all these numbers out. That took a while. But what we're going to do is we're going to follow the scientific notation rules. I'm just going to put SN rules, specifically rule 1. And I need to make all of these in scientific notation. Now, how do I do this? Well, first, I need to figure out where the decimal is going to go. Remember, for D, it has to be between 0 and 1. So the decimal is going to go right here because 4 is bigger than 1, less than 10. For New York, the decimal is going to go right here because 3 is bigger than 1, less than 10. And for Texas, it's going to go behind the 2 because 2 is bigger than 1, less than 10. Now I need to figure out how many spaces, how many place values I'm changing it. Because here's where the decimal used to be. How many place values did it change? Well, count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm moving the decimal 11 place values. So this long number for the debt of California changes to 4.07. I keep all the numbers times 10 to the 11th because I moved 11 place values. So this number is a big number, so it's a positive exponent, and I moved the decimal 11 spaces. Take a minute, pause the video, see if you can change the debts of New York and Texas to scientific notation, just like I changed to California. Okay, you should have paused the video, and if you did the scientific notation correctly, you should have said New York's debt is going to be 3.37 because that matches Rule 1, times to match Rule 2, and how many place values the 10 is going to move? Well, I moved, just like California, I moved 11 place values for New York. And for Texas, you should have had Rule 1, 2.76. Rule 2, multiply. Rule 3, base of 10. And how many 10s did I move? How many place values? How many spaces did I move the decimal? 11 spaces again. So now, instead of this addition problem, we have an addition problem with scientific notation. You might be saying, how do we do this? Well, this is where your knowledge from 6th and 7th grade come in of the different properties. Specifically, I'm going to use the distributive property. We have talked about it before. I know you learned it in 6th and 7th grade. Distributive property is when I can pull out a common factor. I take something we're multiplying by and I pull it out. So for example, I see in every debt, 10 to the 11th is all of them. So I'm going to pull out 10 to the 11th. So what's left is just the decimal numbers. That's the distributive property. And the 10 to the 11th just comes on the outside. So I have all of these added together and then times 10 to the 11th. So the next thing you just do, add the three numbers together. And this is a lesson where I'm okay if you have a calculator. If you want to use a calculator for some of these addition and multiplication, that is okay, because the main focus is, do you know how to do the scientific notation work, not can you add. So when you add these three numbers together, you get 10.2. And then we can keep the times 10 to the 11th. Now you'll notice a problem with this, those of you paying attention to the rules, because you'll see that this answer does not follow Rule 1, because 10.2 is greater than 10. So we need to fix this. What I'm going to do is I don't want the decimal to be here I want the decimal to be one space over right here, because I need to follow rule 1 when I do scientific notation. So because I'm moving the place value, I'm moving the decimal again, the place value is changing, so the order of magnitude has to change. Let me show you what this looks like when we write the number out. 10.2 times 10 to the 11th looks like this. This is the real number after I jump 11 spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's 11 spaces away, 11 place values away. When I put the decimal here, I'm putting another place value right here. So it was 11 spaces away, and then I moved it one more. So now it's 11 and 1, 12 spaces away. So when I put the decimal here, I move it another place value, so it turns to 10 to the 12th. And that is scientific notation, because now 1 is bigger than 1 and smaller than 10. So after I find the answer, I have to change it to a scientific notation that matches all the rules. And hopefully you saw how I did that. We will do it again for part B, because part B is asking us to do the exact same thing as part A, only this time we're going to do the sum of the debts of the 3 least populous states. So if you feel confident after part A, pause the video and try part B on your own. If you don't feel confident yet, you can keep going with this and I will explain it live. If you feel confident, feel free to pause the video, come back and check your answers when you're done. But for part B, we need the least populous states, and if I go back and look at the table, I see the 3 least populous states are North Dakota, Vermont, and Wyoming. So to find the sum of their debts, I need to do North Dakota debt plus Vermont debt plus Wyoming debt. And I will copy those debts down when I look at my table. So North Dakota's debt is $4 billion plus Vermont's debt, which is $4 billion, plus Wyoming's debt, which is only the small $2 billion. Now, I need to add these together, and you might say, Mr. Baylor, can't I just use a calculator and add these? And yes, you could do 4 billion plus 4 billion plus 2 billion, and you could get 10 billion. And that's an easy addition to do. But it's not always going to be this easy. We're doing an easy one right now so that you can do the more difficult problems using scientific notation later. So yes, you can do this one mental math. But let's do it the scientific notation way, so that way we get to the ones you can't use mental math on, you know the good strategies. So we need to find. So the first thing we need to do is need to use our scientific notation rules and change these 3 numbers to scientific notation. So the decimals are going to go here, here, and here to match rule 1, because I want the 4 in front of the decimal. And then you need to count how many place values the decimal moves. So the decimal was right here. We're moving it right here. How many place values did it move? And when you do your jumps, you find out that it moved 9 place values. So 4 billion turns into 4 times 10 to the 9th, because it moved 9 place values. For Vermont is also 4 billion, which the decimal moved 9 place values, so that is also 4 times 10 to the 9th. And Wyoming is going to be 2 times 10 to the 9th because the decimal moved 9 place values. For the next step, you'll see that there 10 to the 9th is in every piece, so I can use the distributive property to move the 10 to the 9th out of all three, so that I am left with 4 plus 4 plus 2, everything times 10 to the 9th. To do the next step, you just add 4 plus 4 plus 2, you get 10 times 10 to the 9th. But they want our answer in scientific notation, and that is not scientific notation because it does not follow rule 1. It has to be less than 10. So how do we make it less than 10? We make it a 1.0. But I moved the decimal again, so this is going to change the order of magnitude. When I move a decimal, the order of magnitude changes. Let's do 10 times 10 to the 9th, what it was originally. This is 10. If I make it times 10 to the 9th, I need to move the decimal, and 9th is positive, so I'm making a bigger number. I need to move the decimal 9 place values, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's what the number is. This is 10 times 10 to the 9th. But I need to add another place value because I don't want it to be 10, I want it to be 1. So it moved 9 place values here. To match the rules for scientific notation, I had to move 1 more place value. So to make rule 1, to stay true to rule 1, it has to be 1 times 10 to the 10th. The 9 we started with, and then the 1 more because I had to match rule 1. So that is the debt of all three states there. So for the first part A and part B, you found the debt of the 3 most populous states is right there, and the debt for the 3 least populous states is there. For part C is asking us how much larger is the combined debt of the 3 most populous than the 3 least populous. How much larger means it's a subtraction problem. What is the difference between their two things? So I'm doing the debt from the 3 most populous states, the debt from part A, minus the debt from part B, the 3 least populous states. So you will have to look at parts A and part B to get your answers. So the debt from part A, the 3 most populous states, the answer to part A, 1.02 times 10 to the 12th. Minus the debt from part B, the least populous states, 1 times 10 to the 10th. So that is a subtraction problem we need to solve. Now, you should notice that the exponents are different, which means the place values are different. And when we subtract, place value must match. Place value must match for subtraction. This is why when you subtract decimals, you line up the decimals. You line up your place values. The place value has to match. This place value and this place value does not match. So, but you can make them match. You have to make them match. You have to have the same exponent to do the subtraction. So we need to use our exponent rules to help the place values match. This is from the first part of Module 1, because I'm going to take the 10 to the 12th and I'm going to turn it into a 10 squared and a 10 to the 10th. Because you should remember your place value rules that 10 to the 2nd and 10 to the 10th add to make 10 to the 12th. The 2 plus the 10 make the 12. So now I am closer to letting my place values match because now both of them have 10 to the 10th. But this 10 squared is still messing me up. So let me show, but let's do one piece at a time. 10 squared is 100. And then what I'm going to do is I'm going to combine the 1.02 and the 100. I'm going to combine the 1.02 and the 10 squared. Whichever way is easier for you to think about it. You can think about like an exponent. You can think about it times 100. But what happens when we multiply (1.02) times 10 squared or times 100, whichever way you want to think about it, we get 102 because the decimal moves 2 spaces. And it's a bigger number because the exponent is positive. So the decimal, because the exponent is a 2, the decimal jumps 2 spaces. Or because there's 2 zeros in 100, decimal moves 2 spaces. So we get 102 instead of 1.02. And then after we do that little trick, you'll find that the only exponents left are tens. So now the place values match. So for the next step, just like we did before, I'm going to use the distributive property to pull out, because they both match, I can pull out the 10 to the 10th. So now I have 102 minus 1 everything times 10 to the 10th because of the distributive property. For the next step, you have to subtract. 102 minus 1 is 101 times 10 to the 10th. But this answer still is not in scientific notation because 101 is not less than 10. It has to be less than 10. So we have 101, and there's the decimal. And we're making it 10 place values bigger because the exponent is a 10. So move it 10 place values. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that is the number in standard notation. I do not want it to be this though. I want to give I want the decimal to be there, which is 2 more place values. So I started with 10 place values away from the decimal with that. This gives me 10 place values away from the decimal. And then I gave 2 more. I needed 2 more to follow rule 1. So altogether, the new decimal place is 12 spaces away. And that is scientific notation. That is how much more debt the 3 biggest states have than the 3 smallest states. Take a minute to look at that. Make sure you understood everything that I did so that you can practice yourself for exercise 8. Because exercise 8 is exactly the same as exercise 7, except instead of using the debts, they want us to do the populations. So take a minute, pause the video, and try to get as far as you can on exercise 8 before we come back together to check your work. Okay, you should have tried exercise 8 on your own. And now you're ready to check your work with me. We're going to do exercise 8 part A, which is the sum of the populations for California, New York, and Texas. So we need to go back to our table where we have the information. The information is right here on the table on page 86. And we need to do California population plus New York population plus Texas population. And you could write out the numbers long style with California's population is about 38 million plus New York's population, which is 19 million, plus Texas population, which is 26 million. The first thing you need to do, because this is what we're practicing, change these numbers into scientific notation. The 38 million needs to turn into 3.8 to follow Rule 1, times for Rule 2. And how many place values did the decimal move? It moved 7 place values. New York's population is, in scientific notation, is 1.9 for Rule 1, times for Rule 2, and 10 to the 7th because the decimal moved 7 place values. Texas population is 2.6 to match Rule 1, times to match Rule 2, 10 to the 7th because it moved 7 orders of magnitude. Next thing you need to do, you should have followed the same pattern we did after you follow the scientific notation rules. You need to do the distributive property, just like exercise 7a, where you take 10 to the 7th out of all 3 sections. So you just get the numbers, 3.8 plus 1.9 plus 2.6, and the 10 to the 7th is distributed out of them. Next thing you do is you add the decimal numbers, and this is where it's okay to use a calculator to add those. You get 8.3, and it's just like right here, it's times 10 to the 7th, and that is in scientific notation. So that is the sum of the population for the 3 largest states. 8.3 times 10 to the 7th. You change it to scientific notation, you distribute out, and you add. Let's do the same thing for 8b, only this time it's for the sum for the 3 least populous states. So that is North Dakota plus Vermont plus Wyoming, and again you are using the table on page 86. So writing their populations in standard form, North Dakota is 690,000 plus Vermont, which is 626,000, plus Wyoming, which is 576,000. First thing you should do is you should change these to scientific notation. North Dakota becomes 6.9 times 10 to the 5th. Vermont becomes 6.26 times 10 to the 5th. Plus Wyoming, which is 5.76 times 10 to the 5th. All of them are 10 to the 5th because the decimal moved 5 place values. And then you'll see that all the exponents are the same, so we can reverse distributive property, pass them out. We distribute again, and this gives us the numbers independently. 6.9 plus 6.26 plus 5.76, all times what we pulled out, 10 to the 5th. Now, next step is add the pieces on the inside, and once again, use your calculator. 18.92 times 10 to the 5th, and this is where you might notice a problem, because you need one more step because you need to make it match Rule 1, because 18 is bigger than 10, and it can't be. So instead, we want it to be 1.892, because that matches Rule 1. But when we change the decimal, we have to change the order of magnitude. Remember, there's already 5 here. I gave it 1 more, so it's going to be 10 to the 6th. Because 18.92 jumps 5 spaces right here, and I want to jump one more to make it 1.892. Okay, so now, for part C was a little bit different from exercise 7 because instead of asking what is the difference or how much larger, it's asking how many times greater this is. So this is not a subtraction problem for part C, it's a division problem because what they want us to do is how many times greater is California, New York, and Texas than North Dakota, Vermont, and Wyoming. So to figure out how many times greater, we need to divide. So we take California, the answer for the California, New York, and Texas population, which is 8.3 times 10 to the 7th, and we divide by North Dakota, Vermont, and Wyoming, which is 1.892 times 10 to the 6th. So this is the division problem. What I'm going to do first is I'm going to separate my like terms. I'm going to separate this into 2 separate fractions. I'm going to do the 8.3 and the 1.892. I'm going to separate out the decimals, and I'm going to separate out the exponents. Now you're going to divide both of these separately because it's easier that way. This 8.3 divided by 1.892 I would type into a calculator, and you get about 4.39. 10 to the 7th divided by 10 to the 6th, well, that's an exponent rule. You know that when we divide the same base, we can subtract the exponents. We do 7 minus 6. This gives us 4.39 times 10 to the 1st. Or you can say 4.39 times 10, which means it's getting bigger. This number is changing by 1 place value because the exponent is 1. And it's getting bigger because the exponent is positive. So positive means bigger by 1 place value, which means the decimal is making 1 jump to make the number bigger. So how many times more people are in the most populous states? 43.9 times as many people in the 3 most populous states than in the 3 least populous states. Once again, you might not know how to set up these equations, but after I give you the equation, after I give you the beginning part, can you do all the math and get to the end answer? I will give you the equation. Can you get to the answer? Let's do a little bit more practice with exercise 9. Exercise 9 says all planets revolve around the sun in elliptical orbits. That means they're kind of oval shaped. Uranus's furthest distance from the sun is approximately 3.04 times 10 to the 9th kilometers, and its closest distance is approximately 2.749 times 10 to the 9th kilometers. Using this information, what is the average distance of Uranus from the sun? Well, average is the type of math we're doing. That's the key word there. Average means add them up and divide by how many numbers you add. So there are 2 numbers, the furthest distance and the closest distance. So we need to add both of these numbers, and then we're going to divide by 2 because there are 2 of them. So we're going to do 3.004 times 10 to the 9th plus 2.749 times 10 to the 9th. And there's 2 things we're adding, so to find the average, we divide by 2. Now, the first step you're going to do is the distributive property again, because you'll see that there's 10 to the 9th in both of these up top. So pull the 10 to the 9th out. So in the numerator, you are left with the 3.004 plus 2.749 times 10 to the ninth. And remember, we're still dividing by 2. Then we're going to add the two numbers we have in the parentheses here. The next step is to add, and you should get 5.753 times 10 to the ninth over 2 after you add those. Next thing I'm going to do is I'm going to separate the numbers and the exponents. So I'm going to put 5.753 over 2 times 10 to the ninth. I'm just going to separate out the exponents because it does not matter which order I do this in. And then after you divide, so this was kind of like separating out the like terms. And then I'm going to divide using a calculator, and you're going to get 2.8765 times 10 to the ninth. Don't forget the 10 to the ninth. And that is kilometers. So Uranus's average distance from the sun during its whole year is that. After we add both the furthest and the closest distance and divide by 2, that is the average distance. You might want to take a break right now before you come back for the exit ticket. You might want to try the exit ticket on your own for a little while, and then you could come back and check your work against my work. So if you're back, ready to work on the exit ticket, if you tried it, here's how we're going to check our work. Number 1 says the approximate total surface area of Earth is 5.1 times 10 to the 8th kilometers squared. All the salt water on Earth has an approximate surface area of 352 million square kilometers, and all the fresh water on Earth has that scientific notation. And the question is, how much of Earth's surface is covered by water, salt and fresh? So number 1, how much water is on the planet? How many square kilometers? So for part 1, we don't need the total of Earth, we just need the water. So you are going to add the salt plus the fresh water. So you need to do the salt water, which is 352 million kilometers, plus the fresh water, which is 9 times 10 to the 6th. So I want you to solve this on your own. Pause the video right now, solve it. I'll give you a hint. The first step is you should change the salt water to scientific notation. And then you're going to have to match the place value. And if you use, what exercise was it when we had to match the place value? Looking through my notes. It must have been in exercise 7 part C, we had to match the place value. So go back to your work, go back to my notes, and in exercise 7 part C, we had to match place value. So go back to exercise 7 part C if you don't know how to match place value. So change that to scientific notation, match the place value, distribute, and then multiply. And then you might have to fix it with rule 1. Pause video now and I'll give you the answer when you come back. Okay, if you did everything correctly, you should have found out that the total amount of water on Earth is 3.61 times 10 to the 8th square kilometers of water on Earth. If you did all the math correctly, that is the answer you should have gotten. If you did not, I encourage you to try again. If you still can't figure out, go back and look at your notes. And if you still can't figure it out, reach out to me for some more help. For exercise 2, it's how much of Earth's surface is covered by land. This time we do need the total. we know the total of the Earth, and we know how much water. So we need to do, for this one, total Earth minus all water, salt and fresh. So you're taking the total from the first paragraph, which is 5.1 times 10 to the 8th, and you're subtracting the water we found for part 1, which is 3.61 times 10 to the 8th. So you're subtracting this. Take a minute, try it yourself, subtracting both of those. You will have to distribute the 10 to the 8th, and you'll have to subtract, and you'll have to make sure that you are matching scientific notation. Pause the video, come back in a minute, check your answer. Okay, if you got the right answer, you did the work. This is the amount of land on Earth, not water, is 1.49 times 10 to the 8th square kilometers of land. If you got the right answer, congratulations. If you did not, maybe see what you did wrong. If you cannot find out what you did wrong after checking your notes and trying again, reach out to me for some more help. And then moving on to number 3, how many times greater is the water compared to the land? So how many times greater? How many times greater means we have to divide. You're going to divide the water divided by the land to find out how many times bigger the water is. So you have to use the water number that we found in part 1, which is 3.61 times 10 to the 8th, and you're dividing by the land 1.49 times 10 to the 8th. So that's the division problem. We did do practice division in the exercises. Go back and look if you need a reminder, and then try to solve the equation, and then unpause the video when you're ready to check your work. Okay, after you did this division, you should have found out that there is 2.4 times more water than land. There is more than twice as much water than there is land. Hopefully you got the right answer. If you did, congratulations. If you did not, try again. Go back, check your exercises, check your notes. If you are still struggling, reach out to me for some more help. Also, do not forget, you have the homework helper. They give you reminders about how to do everything, so use the homework helper to help you. And then for more practice today, there is the problem set. 2 questions on the problem set. You can try both of the problems on the problem set. For number 1, it's just asking you to write in scientific notation and then tell me which way you like better. Pause the video now, and then when you come back, I'll give you the answer. Okay, this in scientific notation is going to be 6.8127 times 10 to the 16th, because remember, has to be bigger than 1, smaller than 10, has to be multiplication, and the 16 tells me how many places the decimal will move. For number 2, it's asking the average mass of all 4 planets. Average mass of all 4 planets. So it gives you 4 masses. For the average, what you have to do is you have to add Mercury, you have to add Venus, you have to add Earth, you have to add Mars, and there are 4 planets, so you're going to divide by 4. Now you will notice that the scientific notation, the exponents do not match. So you will have to make the place values match. Remember, exercise 7 part C showed you how to make the exponents match. Go back and check and do that again if you need help. You're going to add all 4 of these, divide by 4. Pause the video, come back, and I will give you the answer so that you can check your work. Okay, if you added all these together, making sure that the place values matched before you added. If you distributed out 10 to the 23rd power, then you added the pieces left over, then you divided by 4, and then you fixed it to match scientific notation, you should have found out that the average mass of the 4 planets is about 2.9531925 times 10 to the 24th kilograms. And that's math with scientific notation. Keep practicing. If you need some help, if you need some more guidance, if you just want me to look at your work, send me an email, send me a picture of your work, and it will happen. If you figured it all out, congratulations. I will see you for tomorrow's lesson.